Hi, everybody. Good afternoon. Welcome on back. I thought I would take a minute this afternoon to talk with us for a few minutes about precipitation reactions, which fall under this broader class of reactions that we look at called metathesis reactions or exchange reactions. And take just a second to show you how we represent those sometimes in equation form. So far, every time we've written chemical equations, we've written what are known as molecular chemical equations. And today, I want to introduce you to the idea of writing something called an ionic equation, okay? I think what we'll do is we'll start with a chemical reaction, an actual demonstration, a pretty common one that many of you perhaps have seen. Maybe you saw this when you had Mr. Rumpy as a teacher, or maybe not when he was a teacher, but maybe or rather what you actually performed it yourself. I've got two solutions here of strong electrolytes. I've got some lead nitrate here in this bottle. I'm just going to pour some of that into this beaker here. You can see it's got a nice clear nature to it. It looks like water. You wouldn't want to drink it. It's not going to taste like water. And then I have some potassium iodide, and I'll pour some of the potassium iodide into this beaker as well. And what you'll notice is, got a bit of a reaction going on there. I've got some older stuff going on there, that's for sure. All right, well, this will still work. So anyway, you got these two solutions. Both of these solutions have their species in ionized or dissociated form. So this has got the potassium and the iodide ions in solution. They are solvated, as do the lead and the nitrate ions. Everything is solvated here. These are both strong electrolytes. If I pour this guy into that one, oh baby, that's pretty cool. We get that magnificent bright yellow color to form. That color is the result of a solid that's insoluble, and that's the hallmark of a precipitation reaction. I started with two solutions where all the species were solvated or in solution, and I ended up with a product that is insoluble, okay? Insoluble as a solid. And it's insoluble because the two ions that make this compound up have such a strong attraction for one another that the water molecules aren't able to solvate the compound into its component ions, okay? And that's true for all precipitation reactions. If you think back to the 2 weeks we had in class together, goodness gracious, that wasn't very long, was it? We did manage to start one lab where we created a precipitate, and that precipitate was, there we go. That precipitate was formed through the same sort of a process as what we just saw back there. It's a precipitation reaction, or it's part of a broader class of reactions called metathesis reactions. Now, what we just saw happen back there with that demo this afternoon, we saw the formation of lead iodide. Lead iodide is PbI2, and it's a solid. That was our precipitate. It formed because the lead ions with the +2 charge in solution, right? In solution, and the iodide ions in solution have such a strong affinity for one another. They want to be close to one another with so much force that water isn't able to break them apart. And so when they do come together to form the compound lead iodide, it's in solid form, and you can't get it to dissolve under standard conditions, okay? Well, as I mentioned, precipitation reactions are part of a broader class of reactions called metathesis reactions. And if it's okay with you, I'm just going to abbreviate reaction RXN''S, That saves me a little bit of effort writing, and you at home as well if you're taking notes. These are also sometimes referred to as exchange reactions. So you'll see both of those terms. And the reason they're called exchange reactions is because the cations in the reactants end up exchanging the anions in the chemical reaction. Oh, my S is a little, there we go, that looks more like an S. We can represent that generically with this equation here. AX plus BY ends up producing AY plus BX. And it doesn't take too much effort here to notice that my cation A and my cation B have simply switched the anions X and Y with one another, okay? Now, sometimes this exchange of anions between the cations produces a solid, a precipitate. It doesn't always. In the case of the reaction I demonstrated for you this afternoon, it did, okay? Here's another example of that. You can start with silver nitrate, AgNO3. It's going to dissociate when you mix it with water. You can add that to a little potassium chloride, KCl, also aqueous in nature. The silver and the potassium cations are going to switch their anion partners. So silver is going to end up with chlorine, and that's actually going to be a precipitate. It's a solid substance. It's not going to dissolve. And our potassium is then going to be connected up with the nitrate. And that will go into solution as an aqueous nature. Okay? So precipitation reactions, they follow this pattern, this metathesis reaction pattern, as do, and so maybe I'll write that down, precipitation reactions follow this pattern of AX plus BY gives us AY plus BX, as do many neutralization reactions that we'll start to look at that occur between acids and bases. We'll start to look at those not in section 4.2, but in section 4.3. So the big idea so far is we can, in solution, have a situation in which the cations exchange anion partners, and we can get a precipitate, a solid substance that won't dissolve, to form out of that reaction. Okay? Now, I'd like to take a look at the equation, the full equation, for the demonstration that we worked through just a moment ago. So let's just make a little note. We saw this in demo form. It's on tape. You can go back and watch it again. I started with lead nitrate, which has PbNO3 2 as its formula. It's aqueous, so let's add the AQ there to represent the fact that it's in solution. We're going to add that to 2 Ki, also aqueous. And when we do that, I'm going to make my arrow short or else I'm going to run out of space. Apparently I'm writing too large. I'm going to get lead iodide, which is my solid precipitate. And I'm going to get some potassium nitrate, which is in solution. It's aqueous. Once again, if you just take a look, the lead and the potassium, what did they do in this metathesis reaction? They simply switched anions. The lead ended up with the iodine, and the potassium ended up with the nitrate. And it just so happens that lead iodide is not soluble. Okay? There's no great way to know that it's not soluble other than to focus on your solubility rules. And we're in the process of working on those right now. Continue to do that. Commit as many of the solubility rules as memory as you can. It will make life a little bit easier for you on down the road. Okay, well, this equation that I've written here this morning, this whole thing this morning, it's actually the afternoon. Goodness gracious. Ladies and gentlemen, don't expose your future children to lead paint. We call this equation that we've written here a molecular equation. And I'm going to abbreviate equation with EQ, and I think you'll understand what I mean. What any molecular equation shows is all of the species involved in the reaction, all their formulas, but it doesn't necessarily indicate their ionic character. I mean, we've got the aqueous to tell us that the lead and the nitrate ions are in solution and they're solvated, but this equation doesn't tell me the charge on either of the cation or the anion there, or with the lead iodide as well. And so sometimes what we'll do is we'll take an equation like that and we will write it like this. We will split each of the ions into their ionic form. And so here we've got lead with a +2 charge, which is aqueous, plus 2 nitrate anions with a -1 charge, which is aqueous, plus 2 potassium ions with a +1 charge, which is aqueous, plus 2 iodide anions with a -1 charge and is aqueous. I took all of this. I took my lead nitrate, I took my potassium iodide, and I broke them down into their ionic forms. Now notice, this is where knowing the charges on cations and anions really comes in handy. If you can remember that lead carries a +2 charge and nitrate a -1 charge, it makes writing these types of equations much, much easier for us. You don't have to look back at the notes you took earlier. So once again, the more of those charges we can commit to memory, the better off your life is going to be a little bit further down the road. Now, we can do the same thing for our products on the right-hand side of the arrow. So let's go ahead and do that. Now, lead iodide, it doesn't solvate. It does not become ions. So we're just going to write that as PbI2 and a solid. It doesn't have an ionic character to it. Plus 2 potassium with a +1 charge, and it's aqueous, plus 2 NO3s. I'm running out of space. Sorry about that, guys. And it's aqueous in nature too. This type of an equation that we have written, where we show the ionic nature of our compounds in solution, is called a complete ionic equation. Okay? Complete ionic equation. It shows all the soluble, strong electrolytes as ions. Okay? We've broken them all down into ions. Now, notice when we look at this complete ionic equation that nitrate shows up on both sides of the equation, as does potassium. In this kind of a situation, because the nitrate and the potassium are found on both sides of the equation, we can say that those ions are spectator ions. In this particular case, I'll just put a little note that it's our potassium and our nitrates. Spectator ions play no direct role in the chemical reaction, right? I mean, because look, I start with 2 nitrate, I finish with 2. I start with my potassium, I finish with them. They don't appear to really play any sort of a role in this particular reaction, and they don't. And so spectator ions can be canceled. Okay, think about like in algebra class back in the day when you would cancel things on opposites or 2 sides of the equal sign. So I can get rid of my nitrates. I'm going to do that right there. I can get rid of my potassiums. I'm going to do that right there. And I can rewrite what I've got. I've got Pb2 plus aqueous. There's my lead. I've got 2 iodide aqueous. I've got my arrow. And on the right-hand side, all I've got is PbI2, and it's a solid. That's my precipitate. This reaction here, where I've gotten rid of all the spectator ions, I've gotten rid of all the species that aren't playing an actual role in the reaction, this is called a net ionic equation. And it only has the ions that are playing a direct role in the reaction, right? In my beakers, when I did that demonstration, the nitrates and the potassiums, they're in solution, but they don't do anything. They stay solvated. They're just hanging around, right? Having a good time in the beaker. It's only the lead and the iodide that play a role in the production of this lead iodide, this precipitate that we see right there. That's called, once again, a net ionic equation. Okay? Now, in a net ionic equation like the one that we have here, it's important that our charges cancel one another out. Notice that my lead iodide is going to have a net charge of 0. So my charges on the left-hand side of the arrow also have to total up to 0. Well, I've got 2 positives. I've got 2 negatives. Clearly, that totals up to 0, so I'm good there. The only other thing I'll say about a net ionic equation is this. If every ion in the reaction is a spectator, then no reaction will occur, right? No reaction will occur if every ion is a spectator. In other words, if you find each ion on both sides of the arrow, there's no reaction that's going to happen. Okay? So there you have it, ladies and gentlemen. A little bit of background information, a little bit of knowledge on metathesis reactions. Precipitation reactions follow that pattern. And when we're dealing with water-soluble ionic substances, it's sometimes going to be handy for us to, instead of using the molecular equation, which is what we're used to doing, but turning that into a net ionic equation, which means turn it into a complete ionic equation, cancel out the spectator ions, and then you're left with the nugget of what's actually happening in the reaction. Okay? I'm going to have you guys practice some of that stuff here as we move forward through this lesson. I'll talk with you in a few minutes about what that is. Until then, peace out.